More and more children are out of school, but parents don't want math learning to stop. They're turning to Mathnasium at Home. Real-time math instruction tailored to your child's exact educational needs. It's the same face-to-face live instruction used in our centers for over 15 years, now on a computer. Your child can keep their math skills sharp, catch up, or soar ahead, from home or anywhere with an internet connection. To learn if Mathnasium at Home is right for your child, visit mathnasium.com/at-home. Mathnasium at Home, changing lives through math.
Good day, everyone, and welcome back to Mathnasium Schoolhouse. Welcome to everyone that will be joining us today. As always, I am Sandra, your instructor for today, and I will be joining you guys on a lesson where we explore 3D figures, which is hopefully what has brought you here to us today. As always, feel free to share your name, the grade you're in if you're a student, and maybe what does bring you here. If it's not 3D figures, maybe it's your love of math, or maybe you've got to know some friends now from these schoolhouse lessons. Definitely let us know who we have here with us today. As always, be prepared with your materials if you feel that you will need them, whether it is to take down notes of anything you learn, potentially want to share with someone afterwards. Maybe there are some exercises, some problems that interest you and you want to save for later. And maybe just follow along for today. Or, as always, do the math with me on your page right in front of you. So go ahead and compile those materials if you don't already have them. We are going to get started very, very shortly. Welcome to, and I hope that I pronounce this correctly, Srikar in 4th grade. Very nice. Hayden, 6th grade. Welcome, welcome. So we're going to be exploring, as the title tells us, 3D figures. We'll briefly review some of the 3D figures we're already familiar with, what we already know about some things that we can do with 3D figures, and I don't want to use the word just yet, but as you can see in the title, we'll explore properties by looking at the nets of 3D figures, and then go above, a step beyond that and explore the space taken up by 3D figures, which is something we refer to as volume. So I'll work off of some foundational knowledge you guys already have on on volume, and also some of the facts that Larry would have introduced you to yesterday when you guys were exploring area. So let's get started. As always, welcome, welcome. I'm seeing a lot of 6th graders today, which is great. This is a wonderful topic for you guys to explore now in your math journey, so that's wonderful. So as I said yesterday, Larry explored some 2D shapes with you, and today I want to take us to quite literally a new dimension, right? So we're going to grow our 2D shapes into 3D figures, right? The world we live in is 3D, so why not take the time to explore these 3D figures, their properties, and the space that they take up. So as I said, we're going to explore identify the properties of our 3D figures, and then see how in the bigger picture, volume fits into this 3rd dimension, right? We know by now, hopefully, if we're in 6th grade, we would have heard of the word volume and know just a little bit about it, which is possibly that it is the measure of the amount of space inside that 3D figure, all right? So for example, I'm going to just, before I show my board, I'm just going to pull up a 3D figure that I have here. Some of you might have seen this for other topics covered in math. To me, right now, it's just a 3D figure. And I know that I can call this actually a rectangular prism, and we can discuss that in just a few minutes, why this is a rectangular prism. I'm just trying to show you all the sides here. Maybe you can figure already why it's referred to as a 3D figure. But in talking about the volume, I can, if I understand that it's how much space is occupied by this figure, or the amount of space inside this figure, I can start to describe the volume by these little guys, which you might have already seen too in the same math discussion where you were using these guys. And I can describe the volume of this blue rectangular prism by talking about how many of these little yellow cubes are within here. And again, we'll explore that in detail today when we look at the volume of not just rectangular prisms, but a lot more other 3D figures. And we're also going to be using the language of volume. So yesterday, if you joined us on Mathnasium Schoolhouse, you would have looked at the language of area. We're taking it, of course, a step further because we're looking at the 3D world, the 3rd dimension, which means we have to add in a 3rd dimension when we talk about the dimensions of a 3D figure. So originally in your 2D world yesterday, you were looking at length and width, which if I just share my board here, you would have looked at, let's even just have a rectangle here, right? You would have looked at length and width, and in that you would have called this the length of this 2D shape. This would have been the width. Larry also introduced you to a little bit more language that you might have seen when exploring 2D shapes, which is base and height. So some of you might see this referred to as base and this as height when referring to a 2D shape. For the purpose of today, just to specify this right at the very beginning, we are just going to use the words length and width because height and base will take on different meanings today in our 3D figures, and we don't want to necessarily confuse ourselves today, right? And I see that actually in the comments below, now in the third dimension, we're working with 3D figures, we have height, and that's precisely right. So if I look at this as just simply a 2D shape right now, I have my length, I have my width, but I know it's a rectangular prism, right? It has some depth to it. It's popping off of my whiteboard. And if I just show you this side here, you can see exactly that. This here is that depth that I referred to. We're going to use a more friendly word today as I believe it's Srikar that helped us out with the word. We're going to call this the height, okay? So this third dimension that we're using today is the height. And base will instead take on this 2D shape, which for us in this particular 3D figure is actually the base of the 3D figure. And we'll just use that terminology a lot today. We'll repeat it so we get very familiar with it if you are not already. That's the language, and that is, just before we begin exploring our 3D shapes, why we measure volume in cubic units, right? So if we're dealing with 3 dimensions, we, as Larry pointed out yesterday, which is extremely important, when we measure area, when we measure volume, we must specify the units by which we measured. And so today we will be referring to them as cubic units. And if we use any other units of measure, we'll make sure that we're indicating that it is the volume that we have found. Okay? There we go. Oh, I can call you Sri if I want. Wonderful. Thank you for making that easier. So now let's explore how do we get, in fact, from 2D to 3D. Let's begin our discussion there. And that's where nets come into play. And if you guys have learned about nets, it is one of my favorite geometry topics, actually, just because I love challenging myself with, being presented with a net and trying to identify what solid, what 3D figure that actually represents, which we'll do a little bit of that today. So as we saw, our 3D figures begin with a 2D shape. As I said, we can call this a base with some figures or a side in others. We'll identify which figures those apply to. And we can begin to name the different sides of the shape with top, bottom, left, front, right. That's something that you might have done in the classroom already. But in doing so, that's where we talk about the net of a figure. So let's look at some of our 3D figures first. To discuss nets, it is best if you know the properties of your 3D figures. So that's what we'll review today. So I'm going to show you 4 of the 3D figures that I have. So I'm just going to present them on the whiteboard right now. And I'd love for you to just take the next minute to just comment the names of the 3D figures, just as you know them. Okay, so I'm going to present them here. I'll show you all the sides. This one rolls. Okay, here you go. So that's the first one. Hopefully you've seen all the sides there. The next one I want to show you is this one. So you see this, but it also has these sides here. That's one side, that's another. So this is my 3D figure here. The third one that I want to present is this one. These are just all the sides. They seem to be all the same. Okay. And the fourth one is this guy right here. It has a pointy top here, this kind of base, and I call that a base because that's by which the side on which it stands. If I choose to stand it this way, sure, I can stand it this way, but then the sides are slightly different. So go ahead and tell me the names of these if you know them. I'm seeing a few. I see someone call one of the figures a triangular prism, a cube, beautiful. Oh, someone said cylinder earlier. I missed that. Thank you. Maybe a few more responses. And then we'll look at the individual properties of these figures. Oh, there we go. I already saw properties though. Again, well ahead of me. So let's see. Someone said cylinder, so I'm going to write that under the correct 3D figure. This is in fact a cylinder. Very good. Someone then said triangular prism, so I'm going to fit that in here. Beautiful. I believe I saw cube, and then I saw pyramid with, I'll just correct your spelling here, Pyramid. That is our pyramid. That's exactly right. Thank you so much for that. Oh, I see someone is talking about a cylinder. Cylinder does apply to someone is talking about a circle. Circle does apply to one of our 3D figures on the board here, and we'll talk about that in a second. So now that we know the names of these figures, let's stick with them a little bit longer, and I'd love for you to tell me some properties of them, okay? Specifically, what I'm most interested in is what are the 2D faces? So what are the 2D shapes you see on the faces of these figures? What 2D shapes make up these solids, okay? For all 4 of these. All right. Beautiful. Thank you for answering the names of the 3D figures. How about you take it a step further and tell me some properties? If you've laid out already, if you've listed already the faces, or if maybe that's too challenging, how about you tell me the number of faces you see, the number of edges, the number of vertices? Maybe that's some of the language you're familiar with when exploring 3D figures. Okay, I see someone comment on a circle. Yes, the cylinder does have a circle at the top. That's the first face we're seeing, right? And there are in fact 2 circles, one at the top, one at the bottom, one at the bottom, one at the top. Okay. I see triangle appearing, circular, rectangle, triangular. Very, very nice. Great words being used to describe. So maybe I'll list them down below the appropriate figures. So with a cylinder, we had circle appearing, and I'm just going to write down, yes, that's true. We have 2 circles, and how about you guys can help me out here, what is the 2D shape that's all around here? All around the cylinder. I keep rolling it between my fingers. Let's see if I think someone said earlier rectangle, which is exactly right. If I could possibly take this foam 3D figure and cut it up and just kind of layer, if this was a sticker maybe, and I kind of peeled it off from the outside, it would reveal for me, sorry, I keep moving away from the camera, it would reveal for me a rectangular sticker, right? Imagine maybe a can of soup, if you've seen that, and it has a label all around it. If I peel that off, it comes out to be a rectangle. So this is composed of 2 circles and 1 rectangle. Okay, maybe one of the more difficult 3D figures, that's fine. We got that out of the way. How about a triangular prism? You guys are telling me that there is a triangle involved, which is right. In this case, it's a triangular prism because of exactly the triangle, right? There is a triangle at the 2 bases. So if I just look at it as the top and bottom, I have 2 triangles, and the other sides are, maybe you guys helped me out already, the triangular prism. The prism helps us understand, there we go, someone said rectangle, yes, that there are rectangles all around that, connecting those 2 bases, right? And in this case, because we had triangles at our bases, we have 3 rectangles. How about a cube? What 2D shapes is it composed of? And I believe I saw it. There we go. Sanjeev helped me with the cube. The cube has 6 faces. They are exactly what? There are 6 faces, but what types of faces? I don't think I saw it just yet. What's the special thing about the cube? I said earlier they look like they're the same. So I will say that they are in fact the same. What are they for a cube? Squares. Thank you, Tanya. That's right. So a cube has 6 squares that make up its sides. There we go. Thank you, Lavanya. And last guy here is a pyramid. Before I maybe take that off the board, what can you tell me about the faces, the 2D shapes that make up this solid? In this case, it's a square-based pyramid. Maybe I could specify that on my board too. I can write it's a square pyramid. In fact, the more detailed, the better. That's because its base is a square. Okay? And you guys are saying 6 faces and there's 6... Nope. Sorry, that's wrong. That was for the cube still. I almost saw it. I think you guys are saying 5 faces right before that. Okay, so maybe some of you are delayed in the video. That's fine. That's exactly right. So since I have a square at the bottom here, for every edge of this square, we have a triangle connected to it, giving us let's say 1 square first. You guys can see that. And 4 triangles. All right. Perfect. And then if you guys want to challenge yourself, talk about edges and vertices. Again, something that we can identify when we look at the nets as well. So let's move on from there. What about some shared properties? We looked at the individual properties of these 3D figures. What about some of the shared properties? And I'm going to introduce 2 more figures when we try to sort them into groups. I'm going to introduce a sphere, okay, and a cone. All right, so I'm going to bring that to the board here. I will remove all of this. And how about you tell me some shared properties between these? Okay. What could we say? Maybe I'll start us off with one and you guys can go ahead and share some more. We have some 3D figures that have rounded surfaces, right? Probably most apparent is this sphere. Look at it rolling constantly. It's because it has such a rounded, curved surface, okay? Then we also have a cone. Again, the second figure that we introduced. Thank you, cone and sphere. It has a rounded surface all around, right? It can weirdly roll. And then, of course, our cylinder also, right? It has a rounded surface. So I can put that into a group. Those 2 share some properties. Make sure my sphere doesn't roll away. And then the rest I can say have only flat surfaces, right? Flat, flat, I can sit them on any of these faces. Cube, triangular, prism, pyramid, and there we go. What are some other, yes, thank you for saying it is like a ball. They are all 3D figures, beautiful. That is something that they definitely share in common. Yes, we can find volume of all of them. There's triangles in 2 of the shapes, beautiful. Yes, there are in our pyramid and a triangular prism, very nice. What if I also grouped them into, let me create a few groups here. Let's put cone with a pyramid. I'm going to put the sphere on its own, and then I'll put these ones. What groups have I created here? There are 3 of them. What can you tell me about these? Okay. Well, the sphere is on its own, so maybe I can take care of that one. We already talked about it. It has a curved surface, right? And it has only 1 of them. There's no base, there's no edge, there's no vertex. None of the other figures fit into that group. So I'm just going to take it away. Let's now talk about these 2 groups. What can you see is the same between the figures in each group? These 2 look really familiar, right? They have 2 of these pointy tops, right? And I can also say they have only 1 base, right? So underneath that pointy top is 1 base on which they stand or they sit. And then these other 3 that I have, we can fit more figures into here if I had more, actually have 2 bases on opposite sides. The cylinder we talked about has 2 circles. Cube is very unique. It has 2 squares on opposite sides. If this was a rectangular prism or a square-based prism, rectangular prism, then we could say it has 2 squares on opposite sides, making the bases. And this is very apparent, of course, 2 bases on opposite sides, the triangles, which we already talked about, right? So we can call, and we will call for the rest of today, oh, I'm saying flat faces, very nice, prisms, pyramids, and then we'll leave the sphere alone for now. We'll leave that as a challenge for another schoolhouse lesson. So today we'll look at these 2 groups how to identify them through their nets, their properties, and then finding the volumes of these. And how we can simplify, instead of looking at individual volumes of a cylinder, a cube, a triangular prism, a cone, and a pyramid, we don't want math to complicate our lives. We're here to actually simplify what we know about math, and that's exactly what we'll take away from today. Is if I know properties between these guys, then I can actually very easily find the volume because they have something in common. Okay? So let's start with talking about a net. Okay? So when we unfold, I'm just going to start with the cube. When we unfold, if I had the ability to unfold this cube, the result would be the geometry net of the figure, the net of the figure, right? It is actually the connected shapes that make up the surface of this 3D figure. So in this case, we know the 2D shapes are 6 squares. So my net would be composed of 6 squares. With and under the condition that if I then connected those squares the way that they're connected in the net, they actually formed a closed 3D figure, which in this case would be our cube. Okay? All right. So notice that, again, this is made up of 6 squares. And so if I draw the net, let's say I do that here, I can draw 6 squares, right? And I can just do them in a line. But what is the problem here? Does this form a cube if I just take 6 squares and form them in a line? What do you think? No. Maria says no. Why not? If you can imagine this, and if you want later on, you can take a piece of paper, draw out 6 squares like this, cut it out, and try to fold it safely. You see that you'll have some gaps, right? 2 of the bases, we can say, are unaccounted for. Okay? So I can remove 2 squares and possibly add 1 here, let's say. And let's say I wanted to add 1 here. Okay? And if you want to visualize this in your mind, it'll fold up to be a cube. Okay? Sometimes you'll see some dotted lines in a net where maybe your teacher has given you a net. That shows you where you can fold it up. And just remember that these correspond to the edges, if you've explored edges of a 3D figure. Okay? The nice thing about nets is that all the properties that we explored before can be seen in our nets. So I'm going to pull one up here rather than drawing out my nets. Let's say I have this net here. Go ahead and tell me what 3D figure this creates. Okay, what do you think? We talked about a figure that has 2 circles and 1 rectangle, right? It's composed of these 2 2D shapes. I love that comment there. Thank you. Everyone is smart in their own way. Could not agree more. All right? We're all here to learn. So go ahead and share what 3D figure is created if I take this net and I kind of fold it together. What do you think? Cylinder, thank you for that. That's exactly right. I could imagine myself or visualize in my mind me folding this up, or I can go back to the properties that I know about a cylinder in that there are 2 circles, right? I know that they're also located on the bases. I don't need to know that just yet. And there's a rectangle connecting them, all right? So this is the net of our cylinder. Remember that a cylinder fit into that prism group that we created earlier, right? So we're going to keep that in mind when we explore the volume in just a bit. But remember then that the similarity between those figures that we had was that prisms have 2 bases that are the same shape and size. Okay? All right. So let's practice another one. I am going to give you or draw out, let's say, a triangle here, and I'd like you to tell me, can these shapes make up the surface of a triangular prism? Okay? I'm going to draw these out. Tell me yes or no if this can create a triangular prism. If I had these shapes as the faces of a figure, could this create a triangular prism? Yes or no? What do you know about a triangular prism? We had said something earlier about a triangular prism, and I'm going to cheat here and pull it out, right? We said it's a prism, and so it has two shapes that are the same size and shape on its base, and a triangular prism makes those bases be a triangle. So we need two triangles, and then we need a rectangle connecting all of them, in this case 3 rectangles. Right? Without me even trying to put these together, I can see I have, 3 triangles, making this definitely not the faces of a triangular prism. Okay? Perfect. Let's practice just a bit more. What solid is made if I provide you with these shapes? What 3D figure would be created? I have a square with triangles all around. What 3D figure would this create? Yeah. Thank you, Tanya. Yes, that's correct. So previously we needed 2 triangles. That's right. We had 3. So what about this here? What solid is made from this set of 2D shapes? I have 1 square and 4 triangles. Oh, that reminds me of a figure that we had earlier where we explored the properties. Okay, not a triangular prism if that's what you're answering here. It's actually the square pyramid, right? If I kind of plop it here, that square, a bit smaller, but it's showing there. Thank you, very nice. Thank you, Tanya. And the triangles all around, right? 4 triangles for every side of the square. Wonderful. What if I provide you now, so this wasn't a net just yet because they weren't connected, but it's a step closer. Now I'll provide you with a net. Go ahead and tell me what 3D figure is represented from this net here. And remember what I said about dotted lines. That's where you would fold them. Okay? If you were to fold all along these dotted lines, what 3D figure would be created? So you can visualize it. If you're a visual learner, you love to think in 3D in your mind. You can think about folding these together. Later on after today's lesson, you can ask a parent or someone in your household that could help you print something like this and cut and paste it together. Okay. Oh, sorry, it's Miranda that's answering under her mom's accounts. Thank you. So anytime I've said Tanya, it's actually Miranda. There we go. All right, triangular prism, yay, thank you so much. I see the answer there. That's exactly right. If I were to fold this up, I'd get a triangular prism. That's something I have to keep in mind. But my first step would be, does this satisfy the properties of the triangular prism which we explored before? It does. 2 triangles, 3 rectangles, and then if I visualize folding them together, yes, they connect very nicely to be a triangular prism. Let's try one more. This is a little bit of a challenge. We did see it earlier. What do you think this would form? If I take this net, it looks kind of crazy, but I promise you we could fold it up. It might not be the easiest, but we could do it. What 3D figure would it create? We did see it earlier on the board. Okay. It has a circle as a base. I'm going to start there, or maybe not as a base, I don't know that. But it is the flat shape here that I can imagine it sitting on. Oh, I see Miranda and Lavanya helped me out with a cone. That's exactly right. So just going back to my thought process, there is a circle and then what almost looks like it could be a triangle, but because it's curved, I know it's going to fold all around the circle with the pointed tip, and that creates the cone. Right, if you can see that. This one's a bit of a challenging one, even if you wanted to put it together, but we did it. Last one before we get into volume for today. Let's look at this. It looks like a weird zigzag shape, but I promise you it forms a 3D figure we saw earlier. Because they're squares, it's a version of a rectangular prism. Right? And that would be, you guys are having a nice conversation there. It would be a cube. Right, we have 6 faces that are squares, and we fold this up, which you can try out later on. It does fold up to be a cube. All right, so let's stick with that knowledge and now see how this in fact helps us understand the space taken up by these 3D figures. meaning, as we said before, the volume, right? We understand their properties. Oh, thank you, y'all. Yes, exactly, cubes. Okay, so we said earlier that the volume is the amount of space inside a three-dimensional figure, right? The easiest way to see this, I said earlier, is if I go back to my hundreds block. This is just a very, very basic rectangular prism, something you might have already seen. It's very easy to see the volume that is inside this 3D figure because, as I said, we can denote it using these cubes, right? And if you know anything about this place value block here, there are 100 of these unit blocks, right? These unit blocks, meaning the volume here is 100 cubic units. Another way we can find that is by talking about the 2D base here. We talked about this earlier. The length here, I'm just going to represent it by the L, is 10 units. The width, with the W, is 10 units, right? 10 groups of 10, right? If I look at it as 10 rows composed of 10 units or 10 columns, I get 100, right? 100 square units on this face, but we know that they're the cubes that are composing this shape. And so different ways to look at it. The height here is just one side length of that square, so 1 unit. All in all, that gives us a volume of 100 cubic units, right? And even better than that, we can summarize and say that the volume of any rectangular prism, and I'll write this down for us, is actually just, right, so the volume of a rectangular prism is equal to the base area. Again, we found that to be 100 square units, multiplied by the height, which was just 1 for us, so we didn't really see a major difference when we found the volume versus the area, apart from the units used, right? We know that the area is actually made up of length times width, if you explored that yesterday with Larry. And so other ways you might see the volume of the rectangular prism being shown, described, is it's just length times width times height. Different ways, but it all arises from a very, very basic concept in that we're taking the area of the base and then seeing how many times that appears in the figure, right, which is multiplying the height. Okay, there are numerous visualizations of this. Some of them might actually be very interesting for you to explore, so I absolutely challenge you to take the time to look at that. But let's go ahead and practice with it, right? This is not just so you know the volume of a rectangular prism, but we can take this a step further and use this as the volume of any prism, right? Because we said that there are similar properties between all prisms in that they have 2 bases that are exactly the same size and shape. So let me remove this guy and actually look at some of our figures. I'll leave the cylinder alone for now, but let's look at a square or a triangular prism, right? A square, we could use the same formula. We can find the area of a base, which is a square, and then multiply by how many times that square appears, which is represented by the height. I can do the same thing with my triangular prism. I can find the base area, which we said the base here is a triangle, and then multiply by the height. Right? As long as I know the height, I can multiply by the height to find out how much space is actually occupied by this 3D figure, right? So I want to find out how much this wood-looking figure, how much space it takes up, which is to find the base area and how many times that's repeated throughout this prism. Okay? So let's look at an example. I'm going to erase this here. We'll stick with a triangular prism. Rectangular prisms are cool and all, but triangular prisms are a lot better. Plus, we have one here that we can visualize with. So I'm going to present to you with one. Let's do some of this math together. All right. So I'm going to ask you to find the volume of this triangular prism. So you have a base. I'm going to attempt to draw this here. This is your base of your triangular prism. You have 5 let's say meters here. We don't have to be bothered by the units of measure here. We just need to account for them. And you have, let me just add this here. Okay. So this side length here is 5 meters. This side length here is 5 meters. This side length here is 6 meters. That's just the base, which is the triangle. And then the height of this triangular prism is 10 meters. And I'm just going to include dotted lines here, maybe even in black. All right. Okay, so go ahead and help me find the volume there. You've done this before, very nice. You can definitely help us all out. How can we begin here? I'll use this as a reference if needed, but this is the image here that we can stick with. I see some numbers appearing. So let's start with what we know about the volume of a prism. We said we need to find the base area and then multiply by the height. Lucky for us, we were given the height, good, so we don't have to do any math there. We're just gonna have to end up multiplying by 10, a beautiful number to multiply by. So let's find the base area, right? Let's find the area of this. This does, of course, depend on us knowing how to find the area of a triangle, which if you tuned in yesterday, you would know how the formula for that, okay? So how do we find the area of a triangle? Well, we take half of the base times the height, okay? The key here, which we won't have the discussion today, the key here is that it relies on us knowing not the height of the figure, but the height of this triangle here, right? Which we don't know, okay? We would need to know this height. For some of you, you might have heard of the term Pythagorean or Pythagorean, however you would have heard it before from your teachers in school, right? But in there, we look at we can find the height of a right triangle, right? So I'm going to help you out and say that this height, if you were to use the theorem, is actually 4 meters, okay? But that's something that you have to be able to find using a theorem, okay? Knowing that, we can absolutely proceed with finding the base area. So I'm going to do that here. I'm going to just put it in brackets so we all know this is of a triangle. Okay. It's going to be equal to half times the base times the height. The base we know was given to us as 6. The height we would have found with the Pythagorean theorem, which is 4. So I'm just going to write that in here with a different color. Half times the base, which is 6, times the height, which is 4. And if you multiply that out, I'm not sure if I saw that already, you get 12 square meters because we just found the area. Now to find the volume, we take into account the height, and so the volume, if I just squeeze that in here, is equal to my 12 square meters multiplied by, I apologize if you're not familiar with the dot, I can include my multiplication symbol there. You multiply that with the height, and 12 times 10, as we said, 10 is such a beautiful number to multiply by. We get 120. But remember what Larry was saying to us yesterday, it's not just 120, it's 120 cubic meters because we're dealing with volume today. It's as simple as that. Find the base area, multiply by the height, and you're done. Do not get confused, though, by the different heights that you might encounter in your shapes, all right? Perfect. Let's proceed then. We've looked at the volume of prisms. They follow the same volume formula, which is looking at the base area multiplied by the height. You can tackle that with the volume of a cube using the same method. Rectangular prism, triangular prism. You can go to a prism that has a pentagon as a base, a pentagonal prism, and so on. But let's proceed to a cylinder. Let's see how that possibly differs. So let me erase this here. Right. So we talked about a cylinder being kind of similar to a prism in that it has two of the same shapes on either end, right? So those two bases are the same shape and size. In this case, they're circles, which makes it slightly different than a prism, right? Because it has this curved surface. The beautiful thing, though, is we can approach it the same way when looking at the volume, right? We might have to use a pi, right? Because it involves circles, and circles love to complicate our lives in math. That's what makes them beautiful. Do not ever forget that, right? But it does mean that we have to do a little bit more math in finding the volume, but the approach is the same, right? In that, we look at the area of the base, in this case it's a circle, and multiply by the height, as long as we're given that, okay? And again, if you remember the very basics of volume, it's how much space is in this three-dimensional figure. And so a nice way to think about a cylinder is if you, I don't even know, think of your favorite food that's in the form of a cylinder, and if you slice it up, a cylinder is composed of all those circles you would get from those slices, or even if you think of them as smaller cylinders, and if you glue them together or put them back together or smush them back together, you get this larger cylinder, okay? Just different, like I said, cool ways to look at volume, this space occupied by this figure. So as I said, if we're finding the volume the same way as a prism, let's tackle a problem. So I am going to give you a cylinder. Don't mind my drawings here. Okay. So this is my cylinder. And again, I'm going to include dotted lines for those edges, right? In this case, this curved edge that we don't see. If we have this, and I include some dimensions here, I have 4, let's say, inches as my height, and I have, this might be a weird one for some of you that have not explored circles too much, but this is an important property of a circle that we need to know when finding the area. It's referred to as the radius. It stems from the center of a circle, right, to its outer edge. And in this case, we have 2 inches. Okay, so this is just the radius. For those of you that maybe aren't so familiar with it just yet, we won't take the time to explore it too in depth today, but absolutely circles. And if you're referring to circles being weird and spheres being weird, Sanjeev, I will have to say yes, but there's a beauty about them being weird. So remember that. Circles show up everywhere. So let's find the volume here, okay? So if we're approaching it the same way as before, I want to find the base area. And I've said this already, the base area is of a circle in this case. And so I need to remember the area of a circle, but I do. It's pi multiplied by my radius squared. Okay, hopefully you've seen an exponent before. If you haven't, don't worry. Reach out to your nearest Mathnasium. I'm sure they'd love to introduce you to some of these skills involved here. Okay. So I know my radius. It's already been given to me, so I can just plug that in. So let me do that. I will get pi multiplied by 2 squared, or 2 to the power of 2. Oh, there we go. Someone shared diameter. Very good. So you're very comfortable with circles. Okay. And so we have, what do we have here? The area is 4 pi. I know that the height is already given to me as 4 inches. And I forgot my units there, so let's go back there. It's actually going to be inches squared, square inches. And so if I find my volume, let's use the black there. I have base area multiplied by my height, which means I have 4 pi multiplied by my height, which is 4. Okay, and if I want to add my units in there, I have no problem doing so for the purpose of today. 4 pi inches, or square inches, multiplied by 4 inches, right, which gives me 4 times 4 is 16, so 16 pi cubic inches. There we go. Okay. Perfect. So there we go. Not too scary, right? Just because it involves a circle. So there we go. Now what if we look at pyramids? Okay. So let's look at how do I find the volume of a pyramid? Okay? Some of you might find that prisms and cylinders are so much easier to work with. It just makes a little bit more sense. I do agree with you, but there is a really cool property about pyramids, right? And we can use what we know about prisms to find the volume of a pyramid. So if you want to explore this more in depth after today, or again, reach out to your nearest Mathnasium so they can help you explore this. I know you'll find a lot of interesting information out there. But if you take a prism, let's just take a very standard one, a cube, and we draw from one of its, you might know this as a corner or a vertex, you draw some of your edges of a pyramid, or you connect to other vertices in your cube, you'll form a pyramid, and you'll be able to actually see that the volume of the pyramid that you form is actually, you can see different iterations of it here, a third of the volume of your prism, okay? So long as it has the same base and height. Okay? So let's explore that. Now we know the relation between the volume of a pyramid and a prism. It's just a third of the corresponding prism. So let's look at that. Let's see, for example, if I provide you with an image. So I'm going to give you, I'm going to draw here a cube. So I'll draw my prism first. Okay. And I'll draw my pyramid within that prism, right? So within this cube. So let's say I have just a standard one here. This is the base of my pyramid. And so it's all inside this cube, right? It's just going to the very top here. Okay. So let's say this is a pyramid within my cube, and I know that the prism volume, again, in this case, the cube's volume, is 120 cubic meters. How do I find the volume of the pyramid? What did I say was the relationship between the volume of a pyramid and the prism? You guys can help me out with that. Right? We said that it's just a third. So if I just write that out here, if I know my prism volume, then the corresponding pyramid formed within there with the same base and height, right? It has the same height as the cube and the same base. So the volume of my pyramid is actually going to be equal to 1/3 of the volume of my prism. And if you're very comfortable with your fractions, I'll write this in blue, that means I just need to take 1/3 of 120 cubic meters, right? And I'm very comfortable with my place value. I know 120 could be represented as 12 tens. 12 tens, a third of that, is just like taking a third of 12, which is 4. And if I bring that into the bigger picture here, a third of 12 tens is actually 4 tens, which is 40. And so that's exactly what I have here. 40 cubic meters is the volume of my pyramid. Now that's all dependent on me being given this information, right? What if I wasn't? What if I was just given some of the information of the pyramid itself and not necessarily the prism all around it? So let's see that, right? This is a really cool relationship between them, but it does rely on me knowing the volume of the prism. Okay. So let's say that instead I was given a pyramid that has a base length of 8 inches on this end, and then 6 inches here, right? So it's a rectangular based pyramid, and it extends, just trying to mimic my drawing here. There we go. Sometimes it's really fun drawing these out if you want to try this at home. All right, so there you go. And instead, I'm given, so you can see this triangular face here. If you look at its sides, I'm going to help you out here. Let's pretend that this was the figure I drew. If I look at this triangular face, if I took my red marker and I drew a line here, that's the measurement I'm giving you right now, which is referred to as the slant height, because it's not the full-on height of the figure, right? It's not the full-on height of the figure stemming from the tip all the way to the center of the base. It's actually the height of one of the triangular sides. So here it is 5 meters. Sorry, inches. We're sticking with inches for today, for this exercise, okay? So if we have this information, how can I find the volume of this pyramid? Well, let's see. I know how to find the volume of a pyramid, right? It's going to be a third of the volume of a prism, which is equal to base area times height. So let's see how we can explore that. So volume of a pyramid here is equal to 1/3 of base area times the height. But I don't know the height of my figure, right? I know the base area, I can fill that in. It's just a rectangle, and I know how to find the area of a rectangle. It's length times width. So I know that'll be 8 times 6, 6 times 8. I know that that's 48, so that's good for me. But I don't know this height. That's the problem here. I need to find it because I wasn't given the actual height of the figure, which is what I need. However, if you can visualize this, to find that, given possibly using the slant height, I can actually draw a triangle, and this is where you really have to use your superpowers, right? To visualize cutting up 3D figures. For me, it's a little bit easier, only because I'm very comfortable with 3D figures, and you'll find some of your friends might be, some of them might be not, so you might have to help them out a bit. Some of us are just able to visualize this a little bit easier than others. No problem. But if you can see that there is a triangle that forms in here. And again, relying on the Pythagorean theorem, I can find the height of the figure. So again, we're not going to explore the Pythagorean theorem here, but you can use it to find it, right? Because I have the hypotenuse of my right angle triangle. This will be a right angle triangle. I know the base length because it'll just be half of the length of the base of my pyramid, okay? Which means I can easily find the height using some manipulation of the Pythagorean theorem. When you find that, you'll be able to find that the height is in fact equal to 4, and then you multiply that out. So you'll have 1/3. The base area using the right units of measure is 48 square inches. As I said, use the Pythagorean theorem to find the height of the figure, not the slant height of your figure. And we found that that was 4 inches. And when you multiply that out, you will get 64 cubic inches. Okay. And there you go. Okay. We are not going to carry out finding the volume of a cone, but it does use the same reasoning. In that, if I just provide you with this image here, we know that there is a relationship between the volumes of pyramids and prisms, and we can actually use that same relationship between cones and cylinders, or find a relationship between cones and cylinders, right? And actually when you explore that, so I challenge you to do that on your own today, or again, reach out to someone at your nearest mathnasium to help you out in exploring this. You'll find that the volume of a cone is actually 1/3 the volume of the cylinder, again, under the condition that you're dealing with the same base and the same height, okay? So you're just looking at 1/3 of, remember what the volume of a cylinder was. It was just slightly different from a prism because we're dealing with circles, and so we have to include that special number in math called pi and deal with it there, okay? But again, if we know the volume of a cylinder, if we take the 1/3 of that, we find the volume of the corresponding cone. And similarly, we can find the volume of a cone without knowing the cylinder around it if we know the height and the radius. All right. Another 3D figure that we won't explore today is a sphere, right? We played around with it today. We said that it was the most special 3D figure, if we want to call curved, rounded surfaces special, which fine, for the purpose of today we will. But it does also involve some unique properties, as we talked about, and then, of course, unique formula for finding the volume, which will be saved for another lesson, okay? Challenge yourself, as will be shared in the package with you shortly after today, to explore some of the figures we didn't look at. Take it a step further than a rectangular prism and a triangular prism and look at a pentagonal-based pyramid or prism, right? So pentagonal-based prism or a pentagonal, where the base of this pyramid would be a shape with 5 equal sides, a pentagon, okay? And more, right? That will be it for today. Thank you all for joining me. I had a wonderful time exploring volume, and I hope the key takeaway, as I explained earlier, is that volume, which sounds like such a big topic in math, can actually be simplified to something very easy to deal with if you take the time to explore what these seemingly different looking figures actually have in common. How can you group them and look at their properties that they share in common, and then explore that in their volume, extend that to their volume. Although we haven't looked at surface area today, take a look at what it means to find the surface area of these 3D figures on your own if you'd like, using also the knowledge that you would have gained from Larry's lessons yesterday on area and his upcoming lesson as well. Thank you all, as always, for joining me. Thank you, as always, for sharing your answers. It definitely makes this so much more fun for me. I love to see you guys participating. Have a wonderful day. I will see you at the end of the week again for another lesson in geometry. Take care, stay safe, and smile loads. Thanks, everybody.
It's afternoons that seem to be the most hectic for us, so it was much more convenient when we found Mathnasium at home.
All right, so how do we do half of 5? I think one of the best things about at home is that it really feels like you're almost at home with the student in their house teaching them.
I'm in my comfort zone.
You can just ask for help and the instructor will come right to you.
With Mathnasium at home, I know that they're getting the help that they need.
Awesome, great job.
Mathnasium, changing lives through math.